Hello, this is our harsh environment sensor board. Um, so it's meant to be powered by a battery and report temperature data wirelessly. So I have a little board to read the temperature off this thermistor, and as soon as I power it up, it's gonna connect to a network and report the temperature data. So here's the network I have right now. There's nothing on it, and when I connect it to the battery, it's gonna power on. It's gonna connect to the network. I'm gonna go visit that website or the IP address in a browser, and make sure. Yep. So yeah, that is 72.1 degrees Fahrenheit. That's the temperature in my room. If I put my finger on it to warm it up a little bit, if I refresh it here, yeah, it increased a little bit, but I'm not. Let me try to increase it a little bit more. Yeah, there we go. Okay, but now I'm gonna actually increase it beyond what my thumb can do. So I'm turning on this hot air gun. It's blowing hot air, so I'm gonna point it at it for a few seconds, and I'm gonna read the temperature again. Yeah, so we see 257 degrees, and it will decrease pretty fast. Yep, it's gonna settle around 72. I'm gonna do it again, heat it up again, check the temperature. There we go. Yep. Yeah. And this circuit is pretty much just a thermistor with a 10K resistor and a 100 nanofarads capacitor just to get a little AC noise out. And it's just connected to the analog pin on the ESP32. Yeah, that's our board. Hello guys, this is our project. It's made in Fusion. We made the schematic in Fusion, EagleCAD, and yeah, we also modeled it in Fusion as well because it needs to be put in an enclosure, and we use that for our measurements. So having the 3D model with the PCB was very useful. So here's the schematic. It's designed around the ESP32 and connectivity with another 4G board. Here's the layout. We had a small footprint to work with, so we designed it to be compact and such. And yeah, we had to have a lot of inputs and outputs to be able to read sensors and various things, and work with a battery. So yeah, as well as external like DC voltage, not just 5 volts, but 12 volts, 24 volts, and we need to just be able to convert that for the ESP32 and convert it for the battery and have it be able to work without that and off the battery alone. And so yeah, here's the 3D model of the project. Yeah. and that's it.
Hello, I'm Anthony Cedor. I worked on the harsh environment sensor board. My role was software development and PCB design. I assisted in the verifying the PCB, looking at all the traces, making sure every pin was connected to what it did in the schematic. And once we received the actual PCB and manufactured it, I helped in making sure all the pins were soldered correctly, everything tested electrically, and yeah, I developed the um, testing fixture, and so we can actually showcase it, the demo, and I also developed the software just to work without having to rely on an external server, and because this could be tested inside. Here's the little, uh, here's the PCB research we made, and yeah, here's the little test fixture PCB I made just with a thermistor so we can measure the temperature. But yeah, name's Anthony Cedor.
Hi, my name is Jordan Enger. I was the design lead for the harsh environment sensor board in partnership with Software Logistics. My primary role during the course of the project was as the design lead, and my main function was to just coordinate with Software Logistics to make sure that we understood the scope of what they wanted in their product, and to translate that to the rest of our design team so that we can come up with a product that matched what the customer originally intended. There were multiple phases of the project. Phase one was to design a working prototype, and phase two was to design a more production ready version of the product. So in phase one, the primary goal of this was to just get a working PCB prototype that we can use to evaluate, and based off of the results from that information, we changed the design up a little bit. The main difference between the prototype and the final production version was that the final production version was much more suited to, it was much cheaper, much easier to manufacture, and much simpler. The way we were able to do that was by taking lessons learned from the prototype, and take that and translate it into design changes for version 2. During this entire process, as a design lead, I was taking part in the design as well as working with other members of the group who were designing subsystems to make sure that everything went smoothly and all of our systems worked together well to produce a good, functional final product. Thank you.
Hi, my name is Jasper Everett. I'm the cost and schedule leader for this harsh environment sensor board project. During my role here, I focused on balancing the technical requirements of the board itself with the budget and the timeline constraints. So a key part of this role was selecting the components for the bill of materials. And in that process, I evaluated the performance, cost, and availability of each component, making sure that it met every requirement for our product while also being within the constraints of the budget and fitting in that timeline. Communication in a project like this is very critical. So I coordinated with my team members to align with the specifications and ensuring everything is up to speed. To keep the project organized, I maintain detailed documents of our schedule, updates, and of course, the bill of materials.
Hello, my name is Jess Portera, and my roles on this design team were to coordinate our project and keep our design in line with safety standards. By making sure to get ahead of project deadlines and keep our goal in mind, we were able to design our prototype board version 1 and our production board version 2. Safeties such as overcurrent protection and a battery management system are built into the design of our board to make sure that users are safe in case of any electrical faults.